our next lecture is about register transfer language. So now we will talk about some concept called a microoperation. So a microoperation is an elementary operation that is performed during one clock pulse. It is performed on the information stored in one or more registers. So you can have many registers manipulated in one clock pulse. So we have learned in 348 how to design a register, and you can implement by surrounding combinational circuits, you can implement all kinds of functions. So these functions are, for example, shift left, shift right, serial load, parallel load, clear the registers, or you can increment it. So the register transfer level is a way of describing a computer device. So you have the set of registers, you identify the data transfers and manipulations on the data in the registers. You identify the set of allowable microoperations. This is coming from the organization of the computer. And you also define the control signals that initiate the sequence of microoperations. So we have talked about in the ASM lecture that we had, for example, the control signal that is enabled as depending on the state signal, for example, and some conditional input. And then we were, for example, parallel loading a register in that clock pulse. So the register transfer language is basically a symbolic way of describing this register microoperations. There is no real standard form, but it is a human readable tool for describing the internal organization of the computer. And we can use this to basically facilitate the design process of the digital system. So we have some notation. We are going to call registers names. So we will designate the registers by capital letters. So sometimes you might combine it with numbers. So we can have register R13 or register IR, right? So when we talk about the basic computer, then we will see that there are certain important registers. So there will be MAR register, memory address register, PC program counter, IR will be so-called instruction register. We can show the contents of the register by different conventions. So you can simply have a box that says R1. Okay, so for this one, you don't care too much about what is inside. Okay, so I can do it like this. I can write the individual bits. Okay, so maybe I want to know what is written here, what is written here. Okay, detailed. You show the numbering of the bits. So the least significant bit is 0. The most significant bit is n-1 for an n-bit register. You also can show the subfields, because for later parts of this lecture, we will have a special register called memory buffer register, for example. And this will actually have two parts in it. So the least significant 4 bits will designate an operational code, and the higher order remaining 12 bits starting from 4 to 11, the numbering, will be the address. So then you can refer to this least significant 4 bits by writing MBR of op or MBR of 0 to 3. And you can also say MBR of AD or MBR of 4 to 11 for this part. So we are getting ready for our basic computer notation. But now we are only looking at it like just a normal register. So the basic symbols, actually we did it in the ASM again, right? So we already said that we denote a register with capital letters and numbers. Examples are like this. You can show components of registers with some parentheses. We had this arrow a lot for the ASM, and it shows the transfer. So it shows parallel transfer, for example. R1 is going into R2 in 1 clock pulse. Here we will learn conditional operations. So we will designate the control function P with a column. So it will be like if the control function is returning a 1, then we will do something on some certain register. And we can have a comma if you have more than 1 micro operations in the same clock cycle. So you can do it like this. And we will see here, this is a little bit tricky. Okay? You will think, how is this possible? But we will see how you can do this kind of swap in 1 clock pulse. There has to be, now here is the hint, there has to be some third thing that we don't see, which stores one of these things. So it's like there is, you can think of it as if you are taking 441, there's a swap function, right? So you need a temporary variable to hold one of these things when you are swapping. So there will be something in between. We will see it. It will be a bus or it will be a combinational circuit. But think about it. So the first operation is parallel transfer. Here, the notation is you have this arrow. In 1 clock, the content of R1 is loaded into R2. So the content of R1 is ready in the parallel input of R2. Clock hits and then it's loaded. This is a copy operation. So R1 is not changed. So R1 doesn't lose for parallel load. R1 doesn't lose his content by moving them to R2. Now the control function that we talked about. So there's a control signal. If the signal is 1, then the action takes place. In that case, the notation would be P column R1, R2. So this says that if P is equal to 1, then do the load. Another example, Q prime BA. If Q is 0, then B is loaded in A. So we can look at the circuit for this P. We will have a control circuit. P is produced by it. Now, I connect P to the parallel load, enabling input of R2. Now look at it. So if P is equal to 1, whatever is ready in the parallel input of R2 will be in R2 in the clock pulse. And the timing diagram is as follows. So the load signal is high during clock pulse T. In the transition from T to T plus 1, the transfer happens, like we have discussed in the ASM chart lecture. And of course, in our all circuits, there's a single clock pulse that is controlling the control circuits, control function, and also all the data path, the register components. Some more examples. So here with the control signal P, when P is 1, in the same clock pulse, R5 is loaded in R3 and instruction is loaded in memory address register for some reason. So here both micro operations are in the same clock pulse. How do we do the serial transfer? For the serial transfer, both registers are shift registers. So here, when the conditional as the shift signal is 1, then in that case, here B0 is moved into A3 and B3 is written by a 0. And if you look at AI minus 1, because we are doing a shift right, AI minus 1 is going to be written by AI, and BI minus 1 will be written by BI. Now, for a complete transfer, S has to stay active for 4 clock pulses. That is the word time. We talked about it in logic design. So if you are designing a serial system, then a micro operation can be defined as an operation that takes a word time for execution. So here we can say something like B is replacing A, B is loaded into A. It's actually a serial load, so it will take a word time, and B is loaded by 0, cleared within a word time. We can do more of these shift micro operations. So here, serial transfer shift with an external source. The control signal S is basically enabling this operation. Everything is clocked. So when S is enabled, the n-1 bit of B is 0, and B0 is loaded to A of n-1, and it will go on in this way. So you can basically define these things as shift left A, shift left B here. So here 0 is basically coming from right, shifting left. So it's basically loaded into the least significant bit of B. And B's most significant bit is loading A's least significant bit. We have 2 important shift micro operations. One is logical shift. So here the serial input is a 0. This is basically what we learned in logic design. So it is right logical shift. Here you enter a 0. Left logical shift. Here you enter a 0. And the designation would be R2, shift right, R2, R3, shift left, R3, on the condition that E flip-flop output is 1, shift left A. So you can have this kind of examples. Now we can have circular shift. So here, this is also from logic design. What we have is that if we are doing shift right, the least significant bit will circulate in the most significant bit position, and shift left is the other way around. And we can have such kind of wordings or symbols. So circular shift right, R2 is basically loaded with a circular shift right version of it. R3 is loaded with a circularly shift left version of it. Or on the condition P, you circularly shift left A and circularly shift right B. Okay. So we also have arithmetic shift. For signed numbers, when we are doing these shifts for multiplying and dividing by 2. We talked about it also in logic design. So first of all, we don't change the sign bit, okay, after the shift, because the number sign is not affected by division or multiplication. Whereas in the logical shift, we didn't care, we were just shifting the ones and zeros. If we are doing arithmetic shift left, then it is basically multiplying the number by 2. Don't forget we have a signed number, so the sign stays the same. And we should also check if the leftmost 2 bits differ, because in the other, if that's the case, then it's an overflow. I mean, by shifting left, you are increasing essentially the number, so you can go to a number which doesn't fit into the register anymore, so you can have overflow. So when we look at rules for arithmetic shift, first of all, the sign has to be preserved. For positive numbers, all inserted numbers are 0. For negative numbers, if we have a signed magnitude, the inserted new bits are 0 because it's just the magnitude, okay? So it's essentially the same as the logical shift, keeping the sign. For 2's complement, arithmetic shift left means you are multiplying. Added bits are 0. Arithmetic shift right means you are dividing. Added bits are 1. If you are doing 1's complement, always you add 1, insert 1. So signed magnitude, 2's complement, 1's complement. So now we have examples for the arithmetic shift. So the first example is signed magnitude. So for this one, the sign bit doesn't change and added bits are 0. That's the rule. Now let's look at it. Here, this is a negative number. The sign bit doesn't change. And when we apply arithmetic shift right, we are adding a 0, inserting a 0. So what reads is a -4. Now after the arithmetic shift right, it's -2. Now here this is -2. Keep the sign bit the same, insert a 0. So I'm basically multiplying by 2, becomes a -4. Sign 2's complement, arithmetic shift right, we are inserting 1. The number is this is -6. We are doing arithmetic shift right, keep the sign bit the same, and insert a 1, and this reads as -3. Now we take the same -3, and then we do arithmetic shift left, keep the sign bit the same, we add a 0, and now we get the initial number, which is -6. Now we do one more operation on this. So now another register has 1 0 1 0 -6. I am doing arithmetic shift left. Now what will happen? Keep the sign bit the same and insert a 0. Now what would I expect? This should be -12, but it doesn't fit into this register. So there's an overflow. So you don't get a -12, you get something basically meaningless. So we designed these registers. We actually in 348, and we covered it in the review. So you can implement a universal register with shift micro operations using a multiplexer. So according to the values of the selects, you can do shift left or shift right, and you have to connect the outputs of the register correctly to the inputs of the multiplexer such that they drive the register flip-flops into the correct state. We did this for logic design review. And you can design an arithmetic logic and shift unit. We can see a 1-bit representation of this. So basically, again, we have a multiplexer that we can select arithmetic or logic operations. And with the correct input and output connections, you can see that based on the select, you can realize all kinds of fundamental operations for bit I. And then you put these bits next to each other. So this will basically construct a register that you can do all these operations.